Hello and welcome to a ramble with me. Today we're looking at IEB paper 1 from May 2024, question 8c. The first part of it says, sketch the graph of f of x is equal to ax cubed plus bx squared plus cx plus d, so it's a cubic, and label the turning points and the point of inflection. So the information we're given is that f prime of negative 3 is equal to 0 and f prime of 5 is also equal to 0. So those are stationary points, which could be turning points. Sometimes they could be points of inflection. Then the second bit of information says f of minus 3 is 5 and f of 5 is minus 3. Funny, but essentially when x is equal to minus 3, the y coordinate is 5. And when x is equal to 5, the y coordinate is minus 3. And then we're told that f has 3 unequal roots. So that means that the cubic graph cuts the x-axis 3 times. Okay, so let's get it going. Make this nice and big and bold. Okay, so we know that the points, we have the points minus 3, 5, and 5, minus 3. Okay, and because what do I want to say? And because we've got three different x-intercepts, that already tells me that we're going to have a shape like this, as opposed to something where we have one turning point and then parabola, where did you come from? As opposed to having something like this where your stationary point actually turns out to be a point of inflection. I'm not sure if you can have a turning point and then something like that, maybe, but that would be another situation where your point of inflection is actually a stationary point as well. But then, well, I guess it is possible to cut the, no, you wouldn't be able to, you wouldn't be able to cut the x-axis 3 times in that situation, because the concavity isn't, it would only change from this. Hey, what am I saying? I don't know what I'm saying. Yeah, no, I'm just confusing myself. Nothing new there. So I'm just trying to see if we had a situation like I'm describing, could you have, could your cubic graph cut the x-axis more than twice? And I don't think it can, because this bit would have to lift in order for that to happen, and with the point of inflection it wouldn't, because actually this isn't even changing. So what am I even saying? You have concave down and then concave down again. So what is this situation? This isn't even real. This is not even real. Yeah, concave down and then you continue being concave down. That's just the fake scenario, so never mind that. Yeah, I feel like with the cubic graph, you're either going to have this situation or you're going to have this situation, where you don't have any turning points. Your only stationary point is a point of inflection. And in this situation, you would only cut the x-axis once. Correct me if I'm wrong. Correct me if I'm wrong. Anyway, so back to what we know for sure. is that these 2 points lie on the graph. So I'm just going to quickly plot them. So we have -3 and 5. We'll put you somewhere here. And then we have 5 and -3. Okay, then we know that the gradient when x is equal to -3 is 0, and likewise when x is equal to 5. And we can see that here it would have to be a local max, and this would have to be a local min. So our curve is going to look something like that. Okay, and the point of inflection will be midway between these two, right? So let's say it will be, well, what's halfway between -3 and 5? 5 minus 3 over 2 is equal to 2 over 2 is 1. So presumably somewhere here. As for what the y coordinate is, that's an interesting question. I guess that's also halfway between the this y and this y. So 5 minus 3 over 2 as well, divided by 2. So it will be 1, 1. So there we go. Okay. Next question. If g of x is equal to f of x plus t, then for what? Yeah, okay, I'm slightly uncomfortable. I'm slightly uncomfortable about the assumptions I've made here. So if you already know this from class and you know why it is, move right along, maybe like skip on by another 5 minutes or so, then I'll get to the next part of the question. But I just need to quickly understand why my assumptions would be true. So let me see. The point of inflection. Okay, so let me start with the turning points. The turning points we would find by solving 3ax squared plus 2bx plus c. Okay, so we would find the turning points by figuring out when they are equal to 0. So that would be quadratic. Let's do quadratic formula. So that will be minus 2b plus or minus 2b squared minus 4ac divided by 2a. So those will be our turning points. Okay, so that will be x is equal to minus 2b plus or minus 4b squared minus 12ac divided by 6a. Okay, so that would be where our turning points are at, hopefully. Point of inflection, we'll need to find f double prime. So that will be 6ax plus 2b. And the point of inflection will occur when f double prime is equal to 0. So that is 6ax plus 2b equals 0. And then that would be 6ax is equal to minus 2b. And x would be minus 2b over 6a, which is minus b over 3a. Okay, so now the two things that I want to know for sure is that this point of inflection this x value is indeed the average of these two x values, the x values of the turning points. And you can kind of see that that is true because and the average will be minus 2b minus this over 6a. Okay, so I'm just, for brevity, going to say minus 2b minus the big square root thing over 6a plus minus 2b plus the big square root over 6a, and then we halve that to get the average between the two. So then the minus square root and the plus square root are going to cancel out. Then we're going to have minus 2b minus 2b, which is minus 4b over 6a over 2. So this simplifies to minus 2b over 3a over 2. So if you halve this fraction, you are getting just minus b over 3a, which is indeed the x value of the point of inflection. Okay, so happy with that. Now the second thing I need to figure out is whether the same is true for the y-coordinates. The y-coordinate of the point of inflection. Is the y-coordinate of the point of inflection simply the average of the y-coordinates of the turning points? This is going to be messy now. It's gonna be messy, messy, messy. It's gonna be messy, messy, messy. Hey, 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 hey. Okay, so let's start by finding the y-coordinate, just using this, the x value of the point of inflection. So f of minus b over 3a is equal to, what is this? Ax cubed bx squared cx plus uk. So ax cubed plus bx squared plus cx plus d. Ooh. 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 I cherish the day I am learning. When heaven sent you my way, there's something I've always been searching for, and you bring me so much more. Okay, so now let's get into the real mess. So we need to find the f, the value of f for each of these x values for the turning point. Okay, so I'm just gonna assist myself and copy this across. Everything in me is resisting doing this. Okay, so first off, maybe let me simplify this a bit, because I already see opportunity to simplify. So this is minus 2b plus or minus, I can factor out a 4. So this becomes minus 2b plus or minus 2b squared minus 3ac 6a. So that is, we can now divide through by 2, and yo, tricky bro, what's up? Yammer. Oh, I didn't divide the 6 by 2. Okay, so those are the two x values x coordinates for the turning points. Okay, so now we want to figure out f of minus b, let's say plus this, and f of minus b minus this. Now, to make my life a little bit simpler, I am going to just let m be equal to this guy. Mainly so that I don't have to keep rewriting it, but secondly in the hopes that when I add these two together, the m's can cancel out-ish. That is my hope. Ooh. Okay, so maybe in another color. This is going to be a x cubed plus b x squared plus c plus d. Okay, so that will be a and m minus b cubed over 27a cubed plus b times m minus b squared over 9a squared plus c times m minus b over 3a plus d. I'm gonna leave it at that for now. Okay, I'm just gonna conserve my energy, not expand the brackets unless I'm completely convinced I need to. Okay, and then this guy, so that's gonna be a times minus b minus m over 3a cubed plus b minus b minus m over 3a squared plus c minus b minus m over 3a plus d. Okay, so minus b minus m, I can factor out the minus so that we have minus 1 and then b plus m cubed, and this is 27a cubed. Okay, and similar here, down here we'll have 9a squared. Oh, what are the odds that I'm going to make a careless mistake? Ooh, there's a lot going on over here. Okay, so let's simplify this a bit. So this will be a, actually minus a, and then b plus m cubed over 27a cubed, and this will be plus b because the minus 1 squared will be positive, and then we'll have minus c times b plus m over 3a. Okay, and we just need a little bit of space, guys, for that last little bit over there. So this will be the y coordinate for the second turning point. Okay, so now we want to see if the average of these two gives us this y coordinate that we got over here. Hey, no, not this one. This one. This is the y coordinate. Okay, so let's see. I need yet another page. Okay, so we want to add these together. Okay, so I think I am going to need to expand because, yeah, my brackets be a little different. So let me just quickly do that up here. M minus b cubed is the same as m squared minus 2bm plus b squared times, you know what, actually, I'm gonna just use my Pascal triangle trick. So Pascal's triangle, oh, you know this guy, and so it goes, and so it goes. This actually helps us with binomial expansions, right? Where you have x plus y or x minus y to the power of 10. Instead of doing that multiplication manually, you can just refer to this triangle. This second row here represents x plus the coefficients for x plus y to the power of 1, right? So as you can see, the coefficients are 1 and 1. And then this over here represents the coefficients of x plus y squared. And you know that when you expand x plus y squared, you get x squared plus 2xy plus y squared. So now what that means for us is when you expand x plus y cubed, you're going to have 1, 3, 3, 1. Okay, and then what goes where? So then your x's, you can start with your x or your y. It will go x cubed for the first term, and then x squared for the next one, and then x for the second last one, and then the last one doesn't have an x term. The first term won't have a y, the next one will have a y to the power of 1, the next one will have y to the power of 2, and then the last one will have y to the power of 3. So that will be your expansion, right? So, yeah, I really squeezed that in quite horribly. So let's put this here, like I did for the others. Okay, so how does that help us here? It helps us because now we can say, for the first term, we have a times, so we're gonna have a 1, 3, 3, 1. Okay, so the first term is m, so that will be cubed, and then squared, and then m to the 1, and then no m. Then the second one, and it's very important, you have to include whatever the coefficient of b is. And likewise for m. So if it was 2m, you wouldn't just write m here, you would write 2m to the 3, and then 2m squared, and then, you know, and so on. So here we're gonna have, for the first term, we won't have a minus b. Then the second term, yeah, in fact, I need to really get into the habit of writing the pluses here, man. Okay, so for the second term now, we'll have, I need to move this, first of all. we'll have minus b to the 1. Here we'll have minus b to the 2. And then lastly, we'll have minus b to the 3. Okay. And let's just almost simplify it. So here we can just have m to the 3. Here we have minus b to the 1, so this term is going to become negative. Okay. Right. And then here we have minus b squared, so this becomes a positive term, so it will remain positive. No, I'm not trying to change your size, squared. Okay, and then lastly here we have minus b cubed, so that's going to become a negative term now. Okay, so that's our first one done and dusted. Now to do for the rest. Okay, so the next term is b times m minus b squared. So that one we know is m squared minus 2bm plus b squared over 9a squared. And then this one is c times m minus b over 3a plus, and the d plus d we can already see is 2d. Okay, then we need to do this expansion now. So it'll be plus minus a, so we're just going to make that a negative term one time. So this is again going to be 1 plus 3 plus 3 plus 1 something over 27a cubed. Okay, so we've got everything is positive, so we don't have to worry about signs this time. Phew. So this is going to be b cubed, b squared, b to the 1, no m, and then m to the 1, m to the 2, and then m to the 3. Okay, so now I can just get rid of the unnecessary stuff there. Just move everything closer to each other. Okay. Whew. Wow, this is really going on and on and on. It goes on and on and on. Yay. B, so I'm now on this term. And if you are following along, like doing these calculations as well, good on you. This is exactly how you need to do maths tutorial videos. Like, don't just gawk, follow along, see what mistakes you can catch out before I catch them out, if I catch them out at all. Okay, next term, minus c times b plus m, and then the d's we've already sorted out. Okay, so now I can look at, I want to look at, is this the thickest it gets? Yes, it is. Wow. Okay, so I want to look at, again, it's not even just the top, it's really this whole thing. This guy, and you guessed it, this guy, because they both have the same denominator, they both have a common factor of a, so that is going to be simple enough for me to add together. So this is going to be, we can factor out the a and the 27a cubed. So we're just going to be left with m cubed plus m cubed, so that's going to be 2m cubed. Oh, and it's not a plus. Oh, mistakes are being made. So I need to remember that this term has a negative, so we're minusing all of this stuff. So it's going to be m cubed minus m cubed, so those cancel out. Then minus 3m squared b, m squared b. Okay, so that's going to be minus that one minus that one. So that's going to be 6m squared b, well, minus 6m squared b rather. Then we've got 3mb squared minus 3mb squared, so those cancel out. Then we've got minus b cubed minus b cubed, so that's going to be minus 2b cubed. Okay, so we've sorted out the green terms. Okay, next up I want to look at this guy and this guy, because again they have a common factor of b over 9a squared. So I can factor that out, b over 9a squared, and then now I can just look at what's left. And these are both positive terms, so I don't have to, I'm just adding them together. So we've got m squared plus m squared, so that will be 2m squared. And then we've got minus 2bm plus 2bm, so those cancel out. And then b squared plus b squared, which is 2b squared. Nice. Okay, and then can you guess what are we looking at next? You guessed it. We are looking at this guy. And, ooh, the minus is very important here. Okay, right. We're looking at these two now because they have a common c over 3a. So we're going to factor out that common c over 3a. And we're going to end up with m minus m, so those cancel. And then minus b, so that is going to be minus 2b. And then we've already added the 2d's together. It's getting hot in here. Okay, so let's see what we're working towards here. We want to see if this, well, okay, and we haven't even gotten to the halving yet, because we need to, all we've done now is we've added the two y coordinates together, but we need to average them to see if we're going to get the same y coordinate as we did over here when we just put the x coordinate of the point of inflection into the function. So I am going to strive for an expression that looks like this. I'm going to keep my terms separate. I can already see these denominators in the expression that I'm working with, so I'm not going to try and combine them all into one, so that I can end up with something hopefully that looks like this. So let's see where we're at now. So for now, we have added our two y coordinates together. These denominators look fine, so I'm not, for example, going to cancel out the a's, because then I'm going to end up with 27a squared, whereas in my other expression I have 27a cubed. So I'm going to keep it like this for now. What we want to do now is we want to halve this. So we're going to say half of the sum of the TP's y coordinates is equal to, I'm just gonna straight away halve, like I'm just gonna halve this because they look even already, so that's easy enough. So I'm just typing each term by half, so I'm gonna end up with, first up we have a times minus 3m squared b minus b cubed over 27a cubed plus b over 9a squared, and here we have this factor, so we end up with that, Okay, and then we have half of this factor, so that's going to be, let's just keep it at c times minus b, so I'm just going to actually say minus bc over 3a, and half of 2d will just be d. And now, hypothetically, maybe this is equal to the y-coordinate that we calculated over here. Otherwise, my assumption all this time was incorrect. It was already looking so fishy. I might have assumed incorrectly. Or I might have made a mistake somewhere. You know? Okay, wait. I'm gonna say cut. I'm gonna add one more page, hopefully. Okay, the other thing is that we're hiding a very big expression inside this m. So maybe now it's time to bring it back, because maybe now things will cancel. Because right now, as things stand, we're trying to get to this, or we're hoping that we're going to get to this, right? And right now, we're not really there. The d's are there, minus bc over 3a, that's there. So really, it's these two terms that we're hoping are going to simplify to this. So let's see now if we actually bring back the m, because remember the m was so that we wouldn't have to rewrite this square root all the time. So m is equal to square root b squared minus 3ac Okay, so this is actually then going to be equal to a minus 3, and then this squared will just get rid of the square root. Ooh, it's about to get interesting up in here, y'all. It is about to get interesting. So now we have b times, and again, this will just be b squared minus 3ac plus b squared over 9a squared, and then this term is just minus bc over 3a plus d. Okay, so let's multiply this out now. So this is a times, so this is going to be minus 3b times each of these guys. So, okay, I don't know why I brought out the square bracket, no? So this will be minus 3b cubed plus 9abc minus b cubed. Ooh. Okay, and this will be b times 2b squared minus 3ac over 9a squared. And then these other terms are just out here living their simple life, waiting for this chaos to end. Yo, okay, I shouldn't say this is the last page I'm adding, because clearly my ginormous handwriting is not doing me any favors. Okay, so this is a times minus 4b cubed plus 9abc over 27a cubed. And then here we have 2b cubed minus 3abc over 9a squared. And then we've got our minus bc over 3a. How guys, I'm just going to shrink you now. I can't be going on two lines all the times. Okay, so now if we multiply this out, we have minus 4ab cubed plus 9a squared bc over 27a cubed. Hey, here we have 2b cubed minus 3abc over 9a squared minus bc over 3a plus d. Oh, the chaos of it all. Yeah, I think I'm gonna have to put them over one fraction now, because what must happen? What did we say we're trying to work towards? Let me just remind myself. So we were hoping to get to this. So what I'm gonna do is, since I know that these ones are already here, so I'm not really gonna be concerned about these ones. I'm gonna be concerned about these guys. So I'm gonna kind of ignore these guys for now. So I'm going to put these ones over a common denominator of 27a cubed. So that would mean I need to times top and bottom here by 3a. So that will be 6ab cubed minus 9a squared bc. Ooh. Ooh. It's already looking so interesting. So this is now going to be 2ab cubed, right? Because like terms. And then this is another pair of like terms, which is going to cancel out. So now we have 2ab cubed over 27a cubed minus bc over 3a plus d. What were we trying to work towards again? I forget. So now what I want to do is I'm going to split this term up so that we have a minus ab cubed over 27a cubed. So that would mean I need to say minus ab cubed over 27a cubed plus 3ab cubed over 27a cubed, so that I end up with a 2. And then hopefully that plus 3 whatever is going to simplify to this. Let's see. So I'm going to officially now keep this very nearby because the end is nigh, guys. For those who have stuck around, hi, you are ninjas, and clearly this stuff interests you, so you should consider pursuing it further in life, I think, because it speaks to really enjoying the core of mathematics. The core. Okay, so just to recap what we've done here, we have taken this term and spawned it out into these terms, right? If you add these two together, you will still get this term. But now the nice thing is this term is matching this term. These guys are matching those ones. And now we need to see what this term is going to simplify to. We are going to get minus ab cubed over 27a cubed. Then here we're going to get the 3 goes into the 27 9 times. The a's are going to cancel a bit. So now we're just left with 2 a's at the bottom. And up here we have, lo and behold, b cubed. Oh my gosh, get out. Get out. Oh my word. Oh wow. The beauty of it all. So what we have finally shown after 1, 2, 3, 4, 5, 6, 7 pages of work is that for any cubic curve that looks like this, right? And I think there are a couple of assumptions we need to make. I think we need to, okay, the A obviously has to be non-zero, otherwise it wouldn't even be cubic. What else would we need to assume? It looks like it's just the A really that is interesting. There might be other stuff that we need to assume in order for that to be real. So some more conditions we need to put on there. So, but for the most part, let's just say if A, B, and E, B, C, and D are well behaved, then what we have shown is that the point of inflection is really just then the x coordinate is the average of the turning point's x coordinates, and the y coordinates is also the average of the average of the turning point's y coordinates, the y coordinate of the turning point. Wow, that is really so satisfying to kind of have the maths back the intuition, because kind of visually you can see that, yeah, it kind of feels like this is the midpoint of the line that joins these two. So anyway, now I can confidently say that this is indeed the correct label for the point of inflection. I just took the average of -3 and 5 for the x coordinate, and the average of 5 and -3, which I already knew, of the y coordinates to give me the y coordinate of the point of inflection. Wow, wow, wow. Wow, that was so much fun. Okay, so last question says, if g of x is equal to f of x plus t, so if I take this curve, this cubic curve, and I move it up or down by t units, for what values of t will g have one real root? So in other words, for how much do I need to move this curve so that it only cuts the x-axis once? So let's start by moving it up. If I move it up, boom, that's where we cut it twice. And if I move it further up than that, that's when we only cut it once. If you imagine that this goes on infinity, right? So the key there is to get this turning point over here. And if you move the curve up beyond that, then we will only cut the x-axis once. So that's the one scenario. The other scenario is if we move the graph down. So then we have 3, 3, 3, 3, x-intercepts 3, 3, 3, and again, once the curve only just touches the x-axis, then we have two x-intercepts here and one over here somewhere. So again, imagine that this curve goes on that way, right? And so if you move the curve just below that, then for any t value lower than that, we're only going to have one x-intercept. So those are the two scenarios we need to consider. So the first scenario, again, is we need to move this curve up such that the turning point is above the x-axis. So we need to move it up by more than 3, right? So that the turning point is above the x-axis, and then we only have this x-intercept. So the first scenario is that t is greater than 3. Not equal to 3, because then the turning point will be on the x-axis, so we'll have two x-intercepts. Right, then the other scenario is if we move the curve down such that this turning point is now below the x-axis. So that means that t, we need to move the curve down by more than 5 units. So we need to minus anything smaller, minus anything smaller than -5. Well, not minus smaller, add anything smaller than -5, right? Or minus anything bigger than 5. So -6, -7, -8, -5.01, right? So the way that we can write that is t must be anything less than -5, because then we're really becoming more and more negative, pulling the curve further and further down, so that this turning point is lower and lower and lower, further and further below the x-axis. So these are our two answers. Good. I'm still so chuffed that I didn't make mistakes in that previous very long detour. I'm chuffed and surprised, honestly. So these are our two solutions. Either t is greater than 3 or t is something smaller than -5. Okay, so let's see what the memo has to say about all our endeavors. Our curve is correct, our labels for turning points and point of inflection are correct, and then our answer for number 2 is also correct. Thank you so much for tuning in for this one. I hope that you enjoyed it. I especially hope that you enjoyed us getting our hands very dirty with some very, very nasty looking algebra, but also just the satisfaction of it all coming together, and also just to have the confidence that, you know, the things that I'm assuming, I can actually back myself, you know, I can actually do the maths to back my intuition. So anyway, hope I will see you again for another ramble another time.